So, first, now these equations we discussed in the last lecture, right? And now I want to derive an analytic solution, approximate asymptotic solution of this equation, of this system of equations, where I will consider these two terms as a perturbation. So, if I forget about these two terms, right? Like this. What we get is an equation for BR and a separate equation for B phi. The equations become uncoupled, and each of these two equations can be easily solved, right? It's y double dash plus omega squared y is equal to 0. So, this is the idea of the solution. I will consider the solutions with these two terms removed as an unperturbed solution, and I will develop a perturbation theory for this system of equations, and we shall get a solution, we shall obtain a solution which is fantastically accurate, amazingly accurate, and very useful. So, for the sake of definiteness, I will consider symmetry conditions corresponding to the quadrupole solution. The same stuff can be done for dipoles equally well. I will also consider vacuum boundary conditions, and I will, here I consider the alpha omega dynamo. Exactly the same thing can be done for alpha squared dynamo. Generally, this method is very general. It's as general as any other perturbation method, which all started with quantum mechanics, of course, perturbation methods. So, this is why I want to present it. Even if you will not be interested in solving exactly this type of equations, the method will work for a very wide class of equations. And the solution reduces to calculating integrals. So, in quadratures, it can always be derived. So, I will consider the simplest case of these equations, where alpha is independent of time. Therefore, these equations possess solutions growing exponentially with time. So, dB by T will be equal to gamma B, where B is a function of Z alone. I will be systematically removing all extra zeros, overbars, and everything, just to make my notation as simple as I can. So we are talking about the kinematic stage of the dynamo, but it's a good start. I'm not saying this is the only interesting regime, but by no means. But let's start with something simple to see if we can get far enough. So, just now a technical step. I will introduce new variable just to make my equations more symmetric. In this equation, here, the dynamo number enters this equation, doesn't this one. I want to consider solutions for this modulus of D much less than 1. D will be a small number in my solutions. So, to see clearly that both terms can be then considered as a perturbation, I will introduce this intermediate step. I will introduce this new variable, and in terms of this new variable, this D appears in both equations, and here this is the sine of D, square root of modulus of D times sine of D. I have in mind that in most applications D will be negative. In most applications D will be negative. So, given these equations, with the boundary conditions of the previous page, derive the approximate solution for D, modulus of D much less than 1. This is the problem I will be discussing. The plan is the following. I will represent my equations the following pictorial form. Gamma times vector B is the left-hand side. It comes from dB by dt. Is equal to some operator of order 1 plus this small parameter, root of D, acting on another operator, which I will call the perturbation operator, acting on vector B. And I have an equality sign. The idea is the following. I will first solve the unperturbed equation to obtain my eigenvalues. So that first I will put D equal to 0, and I will solve the resulting system of equations. Here, to distinguish my desired solution from the solution of this boundary value problem, I will call it with small d. I will discover that there are infinitely many eigenfunctions, all with negative lambdas, of course, because this is just a diffusion equation. The solution to this equation can only decay. So all lambdas will be negative. There will be infinitely many of them, and they all form an orthogonal set. All these functions will be orthogonal on the interval 0 to 1. Of course, I can normalize them to make them orthonormal. And then I will, so these are what is known as the free decay modes. These are the decay rates of magnetic field not supported by anything, just subject to diffusion. And then I will search the solution of this equation in the following form. This gamma will be expanded in power series in this parameter epsilon, where epsilon is root of d. This is epsilon. Do I write it somewhere here? Okay, epsilon is defined to be the root of mod d. And b will similarly be represented in a similar series. Here, there are two terms for a simple reason. We shall convince ourselves very soon that the solutions of this system are doubly degenerate. To each value of lambda n, they correspond to linearly independent eigenfunctions. Therefore, when constructing my asymptotic solution, I should take them into account together. So let's see how it works. And that's it. I want to obtain the solution in this form. And I will, of course, truncate this series in a most cruel way possible. So, these are my equations. I immediately isolate the unperturbed operator, which will contain on the diagonal these two derivatives, and zeros away from the diagonal. If I multiply this by the closed vector BR B5, I will get d2 by dz squared BR for the R component, and d2 by dz squared d5 for the phi component. Likewise, these two terms will combine into this matrix, this operator. These dots stand for whatever else I will have here on the right, this operator. And sine of d and root of d, this epsilon is here in this equation. Ah yes, here I define this epsilon, finally. Okay. And for the sake of definiteness, I will, just to make my calculations down to the end, I will assume some specific form for alpha, sine of pi z. You can choose anything you want, if only you will be able to apply the integral, it will be good enough. So, first step, solve the unperturbed equations with these boundary conditions. It's easy to solve, right? I have now dBr by dt is equal to d2 br squared by dz squared. This I immediately replace by gamma br. I have my boundary conditions. It's clear that the solutions of this equation are br is a times sine of root of minus lambda, I said root of minus lambda z plus b cos root of minus lambda z, and then I will satisfy the boundary conditions. So everything is just trivial, And then, from satisfying the boundary conditions, I will determine my eigenvalues, and this is what I will get for the quadrupolar solution. And remember, right, we had a boundary condition. Ah, yes, here it is. D by dz of b for z equal to 0 is equal to 0. This eliminates the sign, and you keep cos, then demanding that cos of minus root of minus lambda is equal to 0, you obtain your lambdas. Just a trivial exercise in ordinary differential equations. Therefore, but there are two types of eigenfunctions. I have now two independent equations. Right? I have another equation. Absolutely identical equation with the same boundary conditions. For b5. It will also have the same solution. b5 will also be equal to c cos of root of minus lambda z. Lambdas are the same, because they have the same boundary conditions. So, what is the correct eigenfunction? Is the correct eigenfunction b? Does it have the components cos B cos of root of minus lambda z and C cos of root of minus lambda z. Is it the correct form of the solution of this system? No, no. Because each equation also possesses an equation b phi is equal to 0. And here, comma, br is equal to 0. Therefore, the correct pair of the solution is this one. This system of equations has a degenerate solution. So every value of lambda, there are two orthogonal solutions correspond to orthogonal solutions. I can easily normalize them to get to this root of 2. It's okay with the degeneracy. In fact, it took for us, when we were developing this solution, took quite enough. It's not obvious, immediately obvious. We first made this mistake and considered the eigenfunction of this form to get into big trouble and nothing good. So, it is a, well, not entirely trivial fact. Correct? Can I continue? Okay. Now, I'm prepared to consider the whole equation. I now have introduced the functions bn and bn dash such that wbn is equal to lambda bn and wbn dash is equal to lambda bn dash. And I will consider the simplest possible, I will include into my series the smallest possible number of terms into my infinite series. Just the two lowest terms corresponding to n equal to 0. So I will search for the solution in the form C naught B naught times C naught dash B naught dash. I cannot just do this. It will be very unfair. These two solutions decay at the same rate. They are absolutely of equal rights. Correspondingly, I will include gamma will be equal to first to the unperturbed value, lambda naught, coming from here, plus the next order term. And here, if you have some experience with these perturbation methods, you can already notice that it's not usual, it's an unusual expression. That my expected solution for B doesn't contain epsilon. My solution for gamma does contain epsilon. So it seems that these two forms are inconsistent. My ansatz for gamma has higher accuracy in epsilon than my ansatz for B. But this phenomenon is well known from quantum mechanics. When you have degenerate energy levels, then the perturbation, the first thing it does, it splits the energy levels. So the eigenfunctions become difference between the non-degenerate eigenfunctions, perturbed eigenfunctions, is of order 1. But the split in the energy levels is still small. So this is a non-trivial feature. This is a non-trivial feature for degenerate systems. That the perturbation in the eigenvalue has higher order in the small parameter than the perturbation in the eigenfunction. So, what I will do, I will substitute these forms into this equation and collect terms of the same order in epsilon. You know what? Let's do it on the blackboard, right? I think I do have some time. Because otherwise it's impossible to understand this formula. You have to do it with hands. Then it's simple, then it's trivial. So I have this equation. Gamma B is equal to WB plus epsilon VB. And B is equal to C naught B naught plus C naught dash B naught dash. And gamma is equal to lambda naught plus epsilon gamma 1 plus epsilon. I could pretend to be a little bit naive than I am and put here some unknown gamma naught. Then the procedure which follows will immediately tell me that gamma naught is equal to lambda naught. So let's plug this back into here. I will get on the left gamma naught plus epsilon gamma 1 C naught B naught plus C naught dash B naught dash is equal to W times this will be equal to C naught lambda naught B naught plus C naught dash lambda naught B naught dash. This is how I defined my B naughts. Plus epsilon V epsilon C naught V B naught. It's this operator acting on this term, plus epsilon C naught dash V B naught dash. Right? Now, there will be terms proportional to B naught, containing B naught. There will be terms containing B naught dash. B naught and B naught dash are orthogonal. So the next step, take a dot product of this stuff, we say B naught, and integrate from 0 to 1. All B naught dashes, almost all, will disappear, and I will get. Or should I first separate terms of different orders? No, let's do it, yes. Let's now separate terms for the y's. I will have gamma naught, C naught, B naught, plus gamma naught, C naught dash, B naught dash, is equal to C naught lambda naught B naught, plus C naught dash lambda naught B naught dash, is this term. And these terms contain epsilon. The terms are for the epsilon. Epsilon, I will not be writing it. Gamma 1 will be gamma 1 C naught B naught plus gamma 1 C naught dash B naught dash will be equal to epsilon C naught V B naught plus epsilon, decided not to write epsilon, C naught dash V B naught dash. Right? Now, take a dot product with B naught and integrate. This term will go, this term will go, and you will get gamma out is equal to lambda naught. This is where I started. Now we can do the same here. Again, I will have here gamma 1 C naught, this will integrate to 1. This will integrate to 0, is equal to C naught integral from 0 to 1 B naught dotted with B naught dz plus C naught dash integral from 0 to 1 B naught dotted with B naught dash. V is a known operator. B naught is a known function. B naught is a known function. It's just an integral which I can calculate. Likewise here. So these are just two constants which you can easily integrate. C naught cancels. I have gamma 1. C naught, okay, yeah, true. C naught dash. But then, yes, what I will do next, I will now do the same, but I will dot with B naught dash. Yes, then I will get a system of equations for C naught and C naught dash. Two equations. Yeah, absolutely correct. Right? Now let's see. It's here on the slide. Now it will be easier to understand what's written here. So, this is what I'm doing. This system of equations, with this ansatz, I'm trying to solve. I do remember that how the operator W acts on B naught and B naught dash. So, from terms of for the 1, I get gamma naught is equal to lambda naught. It's here. Then from these terms, I have two equations. One obtained by dotting with B naught, the other B naught dash. This equation I believe we have derived. This one, it's this equation, right? Gamma 1 C naught B naught, gamma 1 C naught dash B naught dash, yes, it's this equation. Sorry for my bad handwriting. It's this equation here, written here. Then, this equation we have obtained, this one, where V naught naught denotes this integral involving B naught, V and B naught. V naught naught dash is a similar integral is a similar integral involving b naught, v, and b naught dash. So these are what is called the matrix elements of the perturbation operator. Just two integrals, which we shall calculate in a moment. Fantastic. We have a system of two algebraic equations for two unknowns, c naught and c naught dash. It contains gamma 1, which is unknown. The solvability conditions, the equations are, of course, both equations are homogeneous. The solvability condition tells you that the determinant must be equal to 0. This gives you gamma 1. Done, solved. Cheaply, conveniently, and quickly. And F. We shall see how accurate is this one. So, this is the result you get. So, with alpha equal to sine pi z, you will spend how much? In stage 4 in Newcastle, in the exam, students spent about 30 minutes to make these calculations. Of course, they get, well, they first studied in the class, so if you do it for the first time, it will take probably a couple of hours to make all the possible mistakes and correct them. So you will immediately show that many of these matrix elements are equal to 0. Some of them different from 0. So this will give me, first, gamma 1 will be obtained as square root of pi divided by 2. And the eigenfunction, which was equal to, was equal to c naught b naught plus c naught dash b naught dash. It becomes equal to this. It contains both, right? B naught will contribute the r component, this one. B naught dash will contribute the phi component, this one. How I know this relation? Because in the previous equation, these two equations, I will demand that the determinant is equal to 0. I will obtain gamma 1. Then I will take any of these two equations and find the ratio between c naught and c naught and c naught dash. All absolutely standard. So I know gamma 1, I know their ratio, I know my solution up to an arbitrary constant. And here, this is what is recommended to do when you have degenerate eigenvalues, eigenfunctions. I renormalize now my eigenfunction again. This is why there is no arbitrary constant. I took this solution and normalized it by the condition that the integral. So this tilde, this means this, the integral from 0 to 1 b naught tilde squared dz is equal to 1. This is how I renormalized my solution. This is the normalization. So this completes my first order solution. Not bad, right? It's not impossibly complicated. It's just almost trivial when you do it more than once. When you have done it more than once. You can do second order results on arbitrary order. And here, this is what becomes important. And it took for us quite an effort to make this second order solution, because it's non-trivial. You now, your perturbation, now you are perturbing all the non-degenerate levels, right? So your perturbation to the eigenfunction is already of order epsilon. Likewise, for gamma, there will be perturbation of order epsilon. Again, this is it happens quite often in asymptotic methods, that you know that at each step, you know the eigenvalue to a higher accuracy than the eigenfunction. Sometimes this difference is just numerical difference, but here it's explicit, just in the case of degenerate levels. And it's important that I renormalize this eigenfunction to 1. So I introduced a new unperturbed eigenfunction. Proceed as before. Plug this back. Again, to start with, keep just one term here with an equal to 1, just to see how it works. Plug it back. Dot product with Bn, integrate. Dot product with Bn dash, integrate. Determinant is equal to 0. Find gamma 2. Find the ratio of Cn to C1 to C1 dash. And continue. So everything works like a machine now. You just turn the handle and it gives you banknotes. So the results will be the following. Now you can, having done it once for n equal to 1, after that you can immediately do it for arbitrary n. It's straightforward. Cn can be calculated in a general case where lambda n is clear what is lambda n. Lambda n is here. So n 0 dash. This means that I take my matrix element. Let me write it down. V m m tilde dash. What is there? Tilde is equal to the integral from 0 to 1. B m m tilde dz. In reality, I will be getting here zeros. Only this will be interesting and appearing in the solution. And then these matrix elements, since I have all these sines and cosines, everything is calculated straightforwardly, can easily be calculated. You can show that of all these matrix elements, only few are different from 0, for n equal to 0 and 1. This here, n dash and 0, only 1 for n equal to 0, which is uninteresting. Our series here starts with 1. So I just presented it for the pleasure of calculating the integral. Nothing else. So, all calculations are trivial. And then you get the following, you can calculate C1. All C0 dashes will be equal to 0. You can easily show it. All Cn's will be equal to 0, except for 0 and 1, and 3 except for 0. And this is your solution. Gamma 2 is 0 for any alpha of z. We can just show that this will be identical 0 for conspiracy. Of course, it happens only if you choose alpha proportional to sine pi z. If you choose something different, it will be probably different. So, second order results. This is the form of your solution. B0 we remember how it looked. B1, it's what? B1 consists of cosine here and 0 here. And we can put them together. So cosine of pi z over 2 plus root of the dynamo number, numerical coefficient of order 1, times cosine of 3 times the argument. And I have now my estimate of gamma. Since the term with epsilon squared is identical to 0, the accuracy of this formula is epsilon cubed. Fantastic accuracy. So, is it useful? How accurate is this solution? Oh, now I will return back to my original variables. If I will return back to my original variables, this will be the solutions I get. Br will be proportional to R alpha. B phi will be proportional to root of D. B phi will only contain cos. Br will be slightly more complicated as a function of z. Tangent of k, I immediately calculate tangent of p. Well, it differs from R alpha divided by root of R omega, which we saw before, by a factor of order 1, pi over 4. Now, on the left, I have a graph of this perturbation solution. On the right is the numerical solution, which you can consider as exact. Numerical solutions of the same equations. And I should apologize for not overplotting them. It's just, well, lack of technical expertise. This is how I will explain it. Lack of technical expertise. So, first, I now have an expression for gamma. It's applicable only for D, much less than 1, correct? This is where I develop my solution. But now, I will cross my fingers, close my eyes, and calculate the value of D for which gamma is equal to 0. I will apply this solution where I shouldn't expect the answer to be accurate. D of order 1. The result will be critical dynamo number for which gamma is equal to 0 to the minus 7.8. Numerical solution gives me minus 8. What is this coincidence? The accuracy of how many? 0.2 divided by 10. 2%. Is coincidence or what? I had a solution which is applicable only for D much less than 1. And I get for D of order 10 the result which is accurate within 2%. Okay, let's it's probably luck, just coincidence, right? Let's look at the eigenfunctions. There we shall definitely be in trouble. Let's look at the eigenfunctions. This is d equal to minus 8, just critical value. How b5 looks? It starts with a zero derivative, of course, and then gradually decreases to zero. br starts from a value of the opposite sign, and magnitude is 3 times smaller, roughly 3 times smaller than b5. If you can read it, it's minus 0.5 here, plus 1.5 here. Then it sort of gradually decreases to 0. Minus 8. Here, b5 and br have opposite signs, but it shouldn't worry us. These are linear equations. b5 starts from about minus 5. Minus 5 divided by 3 is sort of 1.5, right? Oh, indeed, it's about minus 2. So the ratio of b5 and br at the origin is quite reasonable. And then indeed, they roughly behave in the same way. But it's easy to behave in that way, right? It's just featureless thing. Let's look at different solutions. D equal to minus 20. I must be mad to consider d equal to minus 20 with a solution which applies for d much less than 1. But again, I want to try champagne from time to time. I want to take the risk. So, how the solution looks now? b5 divided by br is, well, roughly 0.4 probably, right? So 4 times, the ratio is about 4. And look at this now. Now br changes sign. This is interesting. This is a non-trivial behavior. And it changes sign at z equal to 0.6 roughly. And then it goes to 0. Here, it's minus 20 is here. 7 divided by 2. Oh, not too bad, right? It's close enough to factor of 4. b5 again just decreases with z, and br, oh, look at me, it changes sign. Where? Points. Oh. So what's happening? What's happening? How this solution can be that accurate?
How about your 2 pi factors? I mean, Kandu mentioned already that you always get favorable values by multiplying everything.
No, it's a no z approximation. Yeah. Here everything is clean, and no arbitrary factors. No? These are eigenfunctions normalized to unity. There is no arbitrariness whatsoever.
But the decay rate is minus pi squared, right? Instead of minus 1.
Minus pi squared over 2 or something like that, yes. And what?
Oh, I would like it to be minus 1 instead of something funny.
What do you mean funny? Why isn't it funny number?
But unity is even better.
No. It would be a mistake to laugh at pi. It's not funny.
No, you were surprised that you were surprised that something is bigger than 1. But I'm just saying you should be surprised if it's bigger than certain powers of pi squared, maybe.
No. The accuracy of my solution, and this I have derived. It's root of dynamo number 3 halves. No pi's here. This, of course, there is a factor for that. It's order of. For d equal to 10 to the power 3 halves, right? It's sort of square root of 1,000. Instead, I have the accuracy of 0.2%. Pi cannot help, actually. Changing from the accuracy of 3,000% to 0.2%, pi, even pi squared won't help. There's something deeper. There's something deeper here. Why is this solution so accurate? Why, as Matthias explained to us yesterday, this Sokka approximation, which is formally obtained for Rm much less than 1, gives you absolutely reasonable results up to Rm equal to 10.
But in that case, it was really the pi.
No. Of course, 10 is pi squared. But this is not because of pi squared.
And for me, Sokka breaks down at 1. That's exactly what I find. But he has, of course, a different range.
Sufficient condition says small.
Well, Axel,
small compared to 1.
of course, you can choose the units. Such a gravitational constant is equal to 1, rather than 1 over 150 million in CGS units. Of course, I can choose such units. Of course, I can always choose such units that this will be equal to 1. But it doesn't help. It doesn't change anything. The accuracy, the relative accuracy, remains the same, because the difference divided by 8 is a dimensionless number. The difference, 0.2 divided by 8, is a relative accuracy, dimensionless number. It mustn't depend on the choice of units or anything else. If you systematically are doing the same, then the relative difference. For example, if you choose different unit, dynamo number can be multiplied by 2 pi or pi, right? But both will be multiplied by 4. And the relative accuracy will be exactly the same.
Yeah, but you were surprised when it's bigger than 1. I'm just not sure that 1 is a significant number relative to any other.
I will put it the other way around. Then, what is significant is that in my unperturbed solution, they decay. For them, gamma is less than 0. Right? Here, gamma is much larger than 0. So the relative difference between gamma and lambda naught is much larger than 1. Again, I can talk about relative parts. Of course, I can renormalize to have my this gamma equal to 1. But then lambda naught will be equal to minus 10. I can renormalize to get lambda naught equal to minus 1. Well, then this will be equal to 10. The relative accuracy will remain. The relative accuracy will remain. Whatever I do, if I consistent everywhere, if I don't change the rules of the game during the game, then it will be. And I think there is an explanation. And this happens with many asymptotic solutions. They are much more accurate, even beyond the range of formal applicability. Probably what happens is the following. This curve, dashed curve, so this is a schematic form. It's not an exact plot of something. This is my approximate solution. It's accurate enough to the, with respect to the exact solution, say numerical solution, for small d. But deviations can be strong because we can derive asymptotic solution for large diagonal numbers. It should be complementary to this one. And this is just the feature of this particular system. That the two solutions intersect for d of order unity, and they intersect at values of gamma not massively different from the exact. This means that both solutions are accurate far beyond their ranges of applicability. The system is nice. The system is well decorated. This is at the end of the day why it happens. This would look entirely different. Suppose that if I had my exact solution, which is mod of d, right? What I have, mod of d and gamma. Imagine that my exact solution behaved like that. I would do this. My approximate solution would work well here, but here it would mislead me entirely. So what is important is that indeed the exact solution behaves in such a beautiful and simple form. So it's not a coincidence. It's just the property of this simple system. But isn't it amazing that you can obtain a simple solution which has such a fantastic accuracy, just by taking couple of integrals. Continue.
But the exact solution you plotted, is that actually from the numerical simulation? So
Finite differences. Oh, no. In this case, it was a finite difference. It was an eigenvalue problem. This was obtained from eigenvalue problem by solving, discretizing them, and then inverting them. Eigenvalues, finite differences, and then eigenvalue problem. Even where you start seeing significant differences is for d equal to minus 100. For 100, the differences become really serious. You would be worried applying the solution for 100. But 100, I obtained the solution of formula applicable for d much less than 1. And now I'm worried about 100. Now, a few words about how you can move beyond these simple kinematic models. This is now I'm entering in a completely badly explored area full of angry and dangerous animals hiding behind every bush, behind every tree. I call this magnetic Philistian or linear behaviors. So I will just remind you in my own very simple words, what is this helicity constraint? Why everybody is so worried about that? So magnetic helicity is the average value, we can define it as an average value of vector potential and dot product vector potential and magnetic field. These brackets denote integration over volume averaging. Then consider an object where we observe magnetic field, and we have reasons to believe that this magnetic field was produced within this object. So, some long time ago, this object was unmagnetized, or very weakly magnetized. It only had a seed magnetic field, and therefore at that time, magnetic field within this object was almost zero, and together with this magnetic field, the helicity was practically zero. And what is unpleasant about helicity, or maybe pleasant, it's unpleasant to us now because we don't know how to handle this. Later, we shall find, I think after a while, we shall find a very useful instrument like conservation of energy. We now take huge advantage of the conservation law for energy. Very soon, I hope, instead of being worried about conservation helicity, we shall be taking advantage as an additional tool. So this is a quantity which is conserved in ideal MHD, all for high Reynolds numbers. So, if helicity was zero at t equal to zero, it must remain equal to zero now, because it's an integral of motion, and Rm is indeed very high. Now what I will do, I will split magnetic field and vector potential into large scale and small scale fields, and then immediately my helicity will split into the contributions from the large scale field and from the small scale field. Their sum must be equal to zero. I can estimate the helicity due to the large scale field using the galactic, for the galactic environment. It will be of the order of L BRB5. I know that BRB5 is of the order of the pitch angle, 15 degrees. So it's 1/4. 1/4 is the tangent of 15 degrees. The 15 degrees divided by 57 degrees, 1/4. Times L times B squared. I can do the same for the small scale helicity. It's of the order of minus the scale of the helicity, LD, times B small square. It is the scale of the small scale fields, right? These scales come from the fact that B is the curl of A, or A is the curl to the power minus 1 of B. Fine. Let's suppose L, this scale, must be less than turbulent scale. So their sum must be equal to 0. From this I need to get the ratio of B squared to small b squared is equal to 0.4 if only this LD is of the order of the turbulent scale, which is not bad. You showed today, right, from your simulations, that this ratio is the order of 1/2, 1/3, 1/4. Observations give you the same. So perhaps there is no problem with helicity conservation in galaxies. If only this is true. But imagine that this scale of magnetic helicity, which is a quadratic one, is much smaller than L. For example, there are perhaps reasons to believe that this can be as small as scale with Rm. Then you are in. Then indeed you need to get that B squared over the ratio of the energies in the large scale from the small scale must scale as Rm to the power minus 1, being negligible. So this is the problem. This is the problem. This means that the amount of, if LD is small, this means that chi B is small, right? This LD appears here. If this is small by magnitude, this must also be small by magnitude. But the scale is fixed. We know the scale of this field. It's a large scale. Then B must be small. Then B must be small. This, like any other conservation law, conservation magnetic helicity only applies to closed systems. If the system is open, for example, look at this open system, right? If I kick it with my leg, it will move quite a long way away. Its energy will have changed, right? Because it's an open system, because I will have kicked it. the total energy of myself who will suffer from that physically. And this will be considered. Likewise with helicity. We discussed that galactic disks are not a closed system. We saw today these simulations of galactic disks, where this interchange of mass and everything you want between the disk and the halo is so vigorous that very often you have difficulties identifying the disk at all. So, you cannot expect that magnetic helicity will be conserved within the narrow layer which we call disk and where we observe the large-scale magnetic field, which we want to explain. In other words, if you want to consider the balance of magnetic helicity in galaxies, then we must include the exchange of matter and magnetic fields together with helicity between the disk and the halo of a galaxy. And indeed, there are galactic fountains in the Milky Way, stellar winds in other galaxies, where the hot gas moves through the surface at the velocities of the order of 100 kilometers per second or more. This is the velocity of the hot gas which leaves the least vertical. This gas occupies a significant fraction of the area. It will carry with it not only mass, it will carry with it also magnetic field. The helical magnetic field will be carried away vertically from the disk. How much of it will be carried? Magnetic field is frozen to the rough approximation, to the gas. Therefore, the rate of loss of magnetic field will depend on the rate of mass loss. Therefore, we better calculate from this the mass averaged velocity. And this will characterize the rate at which magnetic field and magnetic helicity are diverted from the disk. The ratio of the average gas density to the gas density in the hot gas in the galaxy is of the order of 1% or 1/10%. Then the mass average vertical velocity will be equal to the velocity of the hot gas times the ratio of the two densities plus the filling factor. Here I want to take into account that this hot gas can occupy not the whole disk. Yes, better.
Didn't you told us in the previous lectures that the magnetic field behavior in the galactic plane was not consistent with the frozen
Large scale.
or large scale field? Okay.
And this makes it even more interesting. The small scale field seems to behave almost like almost frozen, except in certain circumstances. For example, in the star formation, very locally, very small scales. Again, there is an evidence that the flux isn't frozen in the field. But the large scale field behaves differently. The large scale field shows all signs of deviations from frozenness. It makes it even more interesting. Small scale field is frozen, large scale field is not. How will it happen? The magnetic field doesn't care about being divided and redivided to large scale and small scale. The magnetic field itself over there doesn't care. So this is exactly what makes it interesting. Small scale field is okay to significant accuracy, depends on time scale. It can be considered to be frozen. So, this is, here I will be relying heavily on Kantor's idea of the volume density of helicity of the small scale of magnetic field. This means that I can consider a partial differential equation of the helicity density, which will contain the helicity flux through the boundary, and I will consider this advective flux. This F is just equal to this vertical velocity, which I have just estimated, this u of the order of 1 to 1 meter second. Then multiplied by time. And then I can convert this equation for the correction to the alpha effect, which will depend on what? On turbulent diffusivity, on alpha itself. This E is, as usual, is equal to alpha B minus beta parallel B. This alpha M is the same, Rm. B equipartition is square root, is equal to 4 pi rho V squared. This is the magnetic field of such strength that the Alden speed is equal to the speed of sound. Then, this is my advection. Plus equations for Gar and phi, which we already seen Exactly the same equation. So now instead of solving 2, I want to be solving 3 equations, which are now nonlinear. And these are the solutions. These are numerical solutions. So what we did, you have this equation, right? Which contains here d by dz. The equations I showed before, these ones, also contain d by dz. So again, we having this experience with these solutions which behave so simply, like cosine of z. This is why the no-z approximation is so good, because the form of the solution is so simple. The solution of this form, indeed, d by dz is up to the correction factor is 1 over h. So we took a no-z approximation for these equations, so that we have the result was that we have a dynamical system d by dt on the left, and on the right you have various terms, various multipliers. And this is then we solve the system of 3 ordinary differential equations. And this is a dependence of magnetic field on time. And this is the Reynolds number based on this vertical velocity. If the vertical velocity is 0, no outflow, then the solution first grows. But when the helicity of the large scale field becomes comparable to the small scale field, it all drops down. It cannot live in this environment. It just dynamo catastrophically. Let's put R equal to 100. Oh, it's slightly better. Keep going, take 0.05. You will get some oscillations. Get 0.3. There will be some oscillations that come the same, but they will be long period. Keep going. Good news. Take 0.8. Gone. It's too much. It's too much. If the outflow is too strong, so that the time scale of the outflow becomes roughly shorter than the dynamo time scale, of course this outflow just destroys the dynamo, and you get unpleasant results, exponential decay. But there is a range of the outflow speeds where the dynamo just happily sits between the catastrophe due to ballistic oscillation and the catastrophe due to the too strong adaptation. So, where are the real galaxies? It would be impossible luck, right, to find real galaxies somewhere exactly within this window between 0.05 and 0.3, 0.1, 0.2. Let's estimate what is the value of R nu. I cannot see it. Let's estimate it on the blackboard. Let's estimate it on the blackboard. So, how am I doing this time? Not very good, but not very bad. So, Ru by definition is equal to this vertical velocity times the disk scale height divided by the turbulent diffusivity. The vertical velocity is 1 kilometer per second, which is 10 to the 5th. I will be using CGS. 10 to the 5th centimeters per second. This h is of the order of 500 parsecs. 500 times 3 to the 18 centimeters. And this beta I remember by heart. It was Oliver was doing an estimate from his simulation today. It's 10 to the 26 centimeters squared per second. This corresponds to the turbulent velocity of 10 kilometers per second and the turbulent scale of 0.1 kiloparsecs. So what we have here, oh sorry, it's 18, 1 parsec. So these two zeros and 18 gives me 20, 10 to the 20th, 10 to the 25th, 10 to the 25th. So this goes, this goes, this goes, and this goes, right? 15 divided by 10, 1.10. Right? 1.10. This is what I expect from this crude estimate. What was the previous stuff? Not too good, right? It's twice this value. I wanted to impress you, but missed this one.
But you don't have the pumping yet, do you?
Huh?
You don't have the pumping. You have downward pumping.
Yeah. It's all crude things. So this is why I'm not worried about this. So the right order of magnitude. If I obtained here 15, I would be worried. If I obtained here all point 15, I would be worried too. But first, the accuracy of this model, just if you forget about physical effects, just the accuracy of this solution, well, it's probably not better than 50%. So, good enough. It's good enough. It's the same order of magnitude as this window for you, where dynamo lives happy life. But what is interesting here is the following. The steady state value of magnetic field, it's the value corresponding to this level. Now, let's see on what it depends. Dynamo number minus d critical, minus 1. This is typical for bifurcation of this type. It's b squared, you get the square root of deviation of the composite parameter from the critical value. Now, let's put Rm equal to infinity. Let's forget about this term. Ru. The larger is the vertical velocity, effective velocity. The larger is the magnetic field. And C is the ratio of the disk thickness to the correlation length. And this is what I like. This formula, unlike all other earlier analytical solutions, is rich enough. In particular, this Ru, the vertical velocity, obviously is related to the star formation rate. Now, I can compare this prediction of this model. It contains dynamo number, which depends on the rotation curve of galaxies. It depends on the vertical velocity, which depends on star formation rate. Now, we shall be able to check if indeed this expression is consistent with observations. This now expression is rich enough in terms of physics to deserve careful comparison. And I hope with Andrew Smith we shall more or less soon be able to report about the results. I hope they will be positive, and we shall be able to confirm that this is roughly there. But if not, okay, fine, anyway we shall report that. We shall see how it goes. But now, this model, at least it's comparable with observations. It can be verified by comparison with observations, and I hope we shall be able to do that. Either to confirm it or disprove it. I can't know what it was. Oh, there are also, well, random magnifier. I will not be spending time on this. I better talk for a short while about the clusters. It will be more interesting. Not much known, for a simple reason. The magnitude in the ISM, in the initial medium, not much is known about them, for a simple reason. Because definitely there will be fluctuation dynamo in the ISM. And the fluctuation dynamos are more or less well explored. We know their properties reasonably well. But the problem is that, so the time scale of this fluctuation dynamo would be of the order of 10 million years, or whatever is the correlation length. This is added over time. But if indeed it's true that the correlation time is shorter than this, as Oliver was telling us today, it can be even shorter. The field is expected to be within robes, flux tubes, not very sharp flux tubes, with a strength of about 5 microgauss within them. It's a competition field. They are expected to have the length of the order of 100 parsecs and thickness of the order of 15 parsecs. This all comes from theory. I would just be just delighted to try to check this with simulations like yours. We shall discuss in the next half an hour the methods to make such comparisons quantitative. The one filling factor of these filaments, probes, should be of the order of 3%. But there are other sources of random magnetic fields. It's tangling of the large-scale magnetic field. It's an independent phenomenon. This magnetic field, this random magnetic field, is supposed to be volume filling. The compression by shock waves, again, it's a separate source. So you have a mess. Magnetic field has more than one source, so it can be difficult, or maybe not. Nobody tried that. It can be difficult to identify physically different contributions to this. But nobody tried it. Maybe it will be easier than I thought. Maybe it's worth taking questions from you now before I continue the clusters. Can I continue?
The bump that we see, I mean, the end of the exponential rise leads to a fairly strong magnetic field.
Mm-hmm.
which is apparently a large-scale field, and then it drops down. I think I should warn that I'm skeptical about the reality of this immediate peak. In simulations we have never seen it, and it's not exactly identified why this model breaks down at that point. The late saturation phase, which then is catastrophically low, that's well reproduced, but not the end of the kinematic stage.
Decay,
The high peak. The peak is actually fairly high.
but let it be, absolutely.
But it's not realistic.
It can be, of course, it's all a simple illustrative model.
But people may take some interpretations out of this that maybe
Yeah.
does
But
really
I know, you see, when using the pointer, I was pointing to here when I was discussing this field, right? Of course, such details shouldn't be taken seriously.
That's even in the direct simulation which you were showing today. The field is growing still, right? It's growing with some kinematic growth rate for whatever reason. Even though, of course, it's a direct simulation. So I would imagine that until the current helicity comes and knocks you out, you're growing. But I agree.
No,
that
Axel
one
talks
line
about
is-
this peak here, without this local maximum, that it can be unrealistic. Here is logarithmic scale, so the ratio of here to here is
No,
significant.
I think you are also worried about the fact that it goes up to 10 to the minus 1 at all,
yes,
right?
and that is not less. I would have thought it could have been less than this, like here, for example.
Axel, again, I won't be worried too much.
Right.
Because it's a very crude model. This only, the conclusion I make from it is that this is worth exploring further. It's worth to spend time on this. If the results here would be negative, I won't even think about wasting my time on a hopeless idea. This tells me that the idea is not hopeless. It doesn't tell me that the problem has been solved. By no means. It's only the beginning rather than the end. But it's good. We have to justify ourselves. Right? So continue to clusters, right? Where is that? Sorry, I haven't prepared it in advance, just forgot. Honestly, I thought that I would have more time for that. But fortunately, I do. Fortunately for me, not for you. So, cluster dynamics. These are entirely different animals. These objects do not rotate. This is a familiar coma cluster, the central part of it. Each spot here is a galaxy, not a star. This is probably a star, a foreground star. All the rest are galaxies. This object doesn't rotate. It cannot host a large-scale body. Let's see, but still, magnetic fields are observed there. There is intergalactic gas. Again, a familiar picture, we saw it before. This gas emits signal emission. So there must be magnetic fields, there must be cosmic rays. We are more interested in magnetic fields because this experience with Faraday radiation measures of background sources seems to suggest that the galaxy clusters, as a rule, possess magnetic fields, but not always cosmic rays. And the general rough summary of observations is that the magnetic field in the clusters is not random. Its scale is comparable to 10 kiloparsecs and strength of the order of 1 micrograms. And here it becomes quite clear why I don't like the term large-scale magnetic field. I'll be calling this magnetic field a small-scale magnetic field, population, right? But its scale is equal to the size of the galaxy. So 5 minutes ago, I was calling this field a large field. And I find myself in a very awkward situation, changing my terminology in just 5 minutes' time. Right? What I was calling large-scale field 5 minutes ago, I will start calling it small-scale.
But that's because the cluster is huge. You are fully tested.
There is more than one reason for that. But I still don't like to be explicitly illogical and irrational. Therefore, I will systematically prefer the words regular magnetic field, mean magnetic field, and random magnetic field and turbulent magnetic field. If I will keep using large scale and small scale, give me a sign, right? Drop a book on the floor, put it in your hand so that I can stop doing that. Okay. So, can we expect any turbulence? Of course, if you want magnetic fields to be generated, there may be some motions. You need to feed magnetic energy. Are there any motions? Is there any, first of all, turbulence, random motions? Yes. Since these clusters are in the process of merger, such violent mergers will unavoidably drive turbulent or at least random motions. But after the end of this event, merger event, the turbulence will start decaying. Because there is no longer source. The merger has happened, and there is nothing else to drive turbulence. So here we have an interesting case of decaying turbulence. Unfortunately, there is no good observational evidence of turbulence. There is some indirect evidence of turbulence from observed pressure fluctuations. So, more or less, inconfidently, people talk about the turbulence scale of the order of 100 kiloparsecs, 10 times the size of the galaxy, roughly 5 times. And the velocity of the order of 250 kilometers per second. It's 1/4 of the speed of sound in that gas. So Mach number of the order of 1/4. I mentioned the possibility of observations of turbulent non-thermal broadening of Doppler lines in future. And we can obtain an upper limit. If there is some turbulence, it will heat the gas because of this energy cascade. And we know the X-ray luminosity, we know how hot is the gas, how rapidly it cools. And of course, the heating rate by turbulence must not exceed the energy emitted by the clusters. This immediately gives you the upper limit of turbulent velocities of 200 kilometers per second. So we were very pleased to see that it agrees very well with independent estimates. So right now it seems that this makes me feel better. It means perhaps that we are more or less, we are not doing entirely silly things.
You should not blame me completely. You are the author of that paper.
Since we published it together, you are responsible for every single estimating. So you cannot avoid the responsibility, no. Objection rejected. So, and the major physical problem here is the following. The mean free path of particles with simply Coulomb interactions is comparable to 5 kilopascals. This is about the scale of the turbulence we are talking about, and about the scale of magnetic structures we want to explore. Again, I mentioned it before. So there is, well, people believe that in magnetized plasma, still we can apply magnetohydrodynamic equations of magnetohydrodynamics. But this is probably the largest caveat in everything I will be saying. That the gas, in fact, is collisionless, but it's magnetized. So, what will happen with turbulence if its energy source is switched off? Normally, if you have a laminar flow, the laminar flow, if you take Navier-Stokes equation, dV by dt, and you make pressure equal to a constant, remove all the terms, so you will be left with a heat equation for V, right? V will decay exponentially. Laminar flows will decay exponentially. Turbulence will not do that. Because turbulence is a non-linear phenomenon. Look what will happen. Suppose I have a turbulent flow with a spectrum, an inertial spectrum minus 5 thirds, say for definiteness, and then there will be some growing part of the spectrum beyond the energy range scale. If the source of turbulence will be switched off, then the energy will be lost, right? The energy will be lost here and not replenished on the left. And there are, well, you can assume that the spectrum of the turbulence will remain as it was, but the level will be decreasing. So, if originally the spectrum was like that, and then after some time it will become described by the dashed line. But look at this. The maximum of the spectrum has shifted to large scales. This means that as turbulence decays, its scale becomes larger and larger. Intuitively, I would think that if something decays, scales will become smaller and smaller. But here's the other way around. The energy range scale will start growing, decaying turbulence just spreads out. Fine. Suppose you have a spectrum, EK, with this E, has the spectrum of K, must be minuses, or pluses. Then S is equal, yes, it's spectrum here, the growing part. Here it is important, will be important, what is the form of the spectrum here. K to the power S. According to various models, it's not a well-defined, not certainly known quantity. There are some models which predict S equal to 2 or 4, the average is 3, some in the other can be important at small, large scales. Anyway, some power law. The total specific energy per unit mass, is 1/2 of V0 squared. The V0 is the maximum velocity, wherever it is. On the other hand, we can integrate this spectrum and get the same energy. K0 to the power S plus 1. Now, we know how the energy will decrease. It's V0 squared divided by T0, energy addition over time, this typical time of the system. And then we have dE by dt depends on V0, but V0 depends on E itself. We get a nonlinear equation. This where from this y exponential isn't a solution. It doesn't. If I had here a constant times E, the solution would be an exponential, like in laminar flow. But I have here V0 is e to the power 1/2, it's e to the power 3/2. It's a nonlinear equation. The result is that E decreases the power law, and this power law depends here on S, on the spectrum in these large scales. So I was at some point fascinated by these arguments, just by that physical statement. The turbulence decays as a power law because it's a nonlinear thing. Turbulence is just intrinsically nonlinear. It is driven by the inertial force in the Navier-Stokes equation, probably. It does need non-linearity. And even the decay, even when dying, it remains nonlinear, stubborn nonlinear.
That's confirmed by simulations, isn't it?
Lots of work on that. It's a classical area of turbulence, both MHD turbulence and dynamical turbulence. Of course, different results give you slightly different values of this is model dependent. For example, if you will consider MHD turbulence and include helistic conservation, it will affect this stuff. Because it depends on how cascade proceeds. So there is a whole range of various behaviors which you can expect. What is important is that it's a power law. This is what I enjoy discussing. That it's a power law. It's not an explanation.
So the Kolmogorov character of the spectrum will be preserved during decay, as I understand.
Yes, yes.
Isn't it? That's a bit surprising because the Kolmogorov spectrum is originally derived with the assumption that you have a certain injection point in the spectrum from which the energy flows down the cascade.
Yes.
Now switch off this providing of energy, and any point in the spectrum is an injection point in some sense.
No.
Yeah, because energy comes from there and flows down, but not only from one point, but from many points. So then,
but at all times it was like that. So this point, right? Imagine that you are sitting here, and all of a sudden engine is switched off. For half of the addition over time, this point will not care about that. You will not know about that, right?
for a while, yeah.
For a while.
But after that?
After that, yes, it will start, everything will start move down. But still, no, at every time, right, maximum energy, it still sits here, at any time. Maximum energy is at the largest scale. So there will be, of course, some energy cascading independently down here, but it will be negligible. It was also happening here, when turbulence was fed at this scale. Still, energy, of course, was lost to the cascade at this
but then it is assumed
but it was negligible.
that it is immediately replenished. So nothing is lost. But if you have decay, then it's on any stage of the spectrum, energy is lost by cascading away. So that's a difference, but you say this is digital.
But still cascading. I think what is important is the cascade. But on the other hand, I think that this statement that the spectrum will remain 5/3. You cannot prove it. It comes from experiments.
Yeah,
I think
that's
it comes from numerical experiments, but you cannot prove it.
Yeah.
You cannot demonstrate this.
The experience.
Yes.
shows.
Therefore, however strongly I will try to argue, my arguments will never be convincing. But at least the experience shows that it's not unreasonable assumption to make. So, there are 3 evolutionary stages in the cluster evolution. The first, most important one, when the cluster is being formed, this takes about 4 billion years, and this is exactly the time when there are many smaller merger events, when the cluster leaves in very violent life. So, during this time, random flow will be volume filling, and we can estimate from the models of structure formation how often the clumps of various masses will be falling down on the cluster. And we estimate that the scale of these motions, it comes from the size of the clumps, which come from models of structure formation, which Kantor knows so well, is of the order of 100 parsecs, and the velocities driven will be over the 300 kilometers per second. The Reynolds number, which we can estimate with the best of our knowledge, is of the order of 100. Perhaps it's enough to drive turbulence. And during this time, there will be a fluctuation dynamo action with a time scale equal to the addition over time here. This means that magnetic field will be amplified by a factor of 3000 during this stage. So it will then, if the initial field was 10 to the minus 9 gauss or stronger, we shall get a field of the order of 2 microgauss and its scale. So this field produced by the fluctuation dynamo, it will be concentrated into robes. So it will of course go further and close to infinity. And the thickness of the robes will be, this will be LD. LD, will be of the order of L0, which is the length or the curvature radius or energy range scale of these robes, times the Rm critical for the fluctuation dynamo, the power minus 1/2. This again comes from a paper of Kantor, which I also like, which is really good paper, but it's not certainly known. There is a large controversy around similar estimates. So I consider it to be correct, but I'm not alone in this world, but there are other opinions as well. So this Rm critical is of the order of 30, so sort of 1/5 of L0. So for L0 of the order of 150 kiloparsecs, you get the turbulent scale of the order of 20 or 30 kiloparsecs. This is the thickness, magnetic scale, with the thickness of these robes. It will produce fluctuation measure comparable with observations. No, but I want to skip it on. There will be all these estimates made for various. The answer is, it seems to work. I want to show you something else. These are breaks of galaxies, let's continue. I want to show you something else, something I think more important. Here, this is the magnetic field produced by the fluctuation dynamo. So we have here a flow which is known as a KS flow, which Andrew Beckley was using. So it's a flow which it has a Lagrangian chaos, and it has a well-defined energy spectrum, and it acts as a dynamo. And there was a significant controversy in the literature about fluctuation dynamos. What they produce: magnetic filaments, ribbons, surfaces, spheres. So what do you see here? What do you think? What fluctuation dynamos produce? Filaments or ribbons? One thing that it depends on your educational level. It can depend on your gender. It can depend on the coloring or the color scheme used. And still people persistently were using all these dangerous naked eye estimates to make far-reaching conclusions. Can we make a quantitative estimate? Can we calculate some number? I'm a simple person. Give me a number. If you want to tell me that something is happening, can you quantify it?
The question is what is being plotted?
Well, isosurfaces of magnetic field, B squared, isosurface of B squared. Yes, so. I want a number.
What will define the sellers?
So what do you think? This is the isosurface of magnetic field produced by the fluctuation dynamo.
No, you got the mark there. Go ahead. So what is it you're trying to sell? Ribbon sheets?
I want to introduce now morphological characteristics which allow you to make an objective morphology. Yes, objective. And there is a readily available tool suitable for that purpose, which is known as Minkowski functions. There is a theorem which tells that the topology of any arbitrarily complicated surface, I think it should be, it's supposed to be convex, in three-dimensional space, is completely, entirely, exhaustively characterized by 4 numbers, which are known as Minkowski functions. V0 is just the integral within the surface. V1 is related to the surface area of the surface. Kappa 1 and kappa 2 are the 2 principal curvatures of the surface. If this is my surface, right, then kappa 1 is the surface along this direction, and kappa 2 curvature along this direction, and kappa 2 the curvature along this direction, like eigenvalues. Maximum, or if you wish, maximum, minimum curvature. So this V2 is related to the mean curvature, the average curvature, and V3 is to the geometrical mean. This is known as the Euler characteristic, a well-known topological measure. So, how to use? Okay, fine, good news. As usual, from what comes from pure mathematics, is very encouraging but useless, right? So, okay, fine. These are supposed to characterize everything, but how? What should I do? Here, pure mathematicians behave differently. They really do something really very useful. You can, first, computing. How to compute this stuff? Especially, well, okay, I can imagine how to compute volume. I can imagine how to compute the surface area. But these curvatures, curvature usually means that I have to differentiate your data, which is unpleasant. But fortunately, it's easy. Again, there are rigorous results. If your data are given on a grid, on say, three-dimensional mesh, then you calculate the volume just by calculating the total number of mesh cubes within the volume of interest. So you just count, right? This is why volume is easy to count. To calculate the surface area, you can just calculate the number of complete edges within your volume, calculate N2, the number of complete surfaces within the volume. Oh no, so V1 is the surface. N2 is the number of faces, minus the number of complete grid cubes, divided by the total number of grid points in the domain. So everything now reduces to counting the number of grid points within the structure, the number of complete edges within the structure, the number of complete faces within the structure, and the total number of grid cubes within the structure, which is a trivial operation. This can be done trivially for any data given on a grid. And then, just manipulating these 3 numbers, you get all 4 integrals, including these 2 which depend on curvatures. The references are all here. All these slides, they're on the web, and the references are here. You will only, yes, you will easily find all these papers. Very illuminating papers. And then, having done this, so we have calculated these 4 integrals. And this is due to Sergei Shamdarin, who used to be in Moscow in the Dovich group, and now he's in Arizona or Kansas? Kansas, right? And Varun Sahni from Ayuga, Pune, where his office is just next door to Kanda's office. They introduced further measures, which can be called thickness, width, and the length of the structures. If you divide volume by surface, you will get a quantity of the dimension of length, which can be identified with the thickness of the structure. This factor 1/2 is adjusted to this formula to work reasonably for simple structures like parallelepipeds. This is the width of the structure, V1, surface divided by the mean curvature. And the length of the structure can be obtained by the ratio of the two curvatures. And you can go further to introduce dimensionless quantities, planarity and filamentarity. If planarity is of order 1, you have a pancake. So planarity is width minus thickness divided by their sum. Is width is equal to thickness, of course planarity will be equal to 0. If width is much larger than thickness, this is what we call a surface. Filamentarity, length minus width. If length is equal to width, you will never call it a filament. But if length is much larger than width, f will be equal to 1, then you will say that I have a filament in my body. What is useful here, that all these measures are integral measures. Automatically, you get the averages over your whole box. The errors will be small because you integrate. You know no way you differentiate the data. So here, well, there is sort of various shapes, and Louise Wilkie, who was a PhD student at that time in Newcastle, calculated planarity and filamentarity for all these structures. Unfortunately, I have no time to discuss it. So what you get? You apply now these measures to calculate the length, width, thickness, width, and length of magnetic structures in that box, which I showed to you. You make a calculation for various values of Fourier rotation measure, Rn, magnetic resonance number. You calculate here, L1, thickness of magnetic structures. They scale very beautifully with Rm in complete agreement with this formula. Next, thickness of the structures. Width, it was thickness, the smallest. Width is the medium. This shows the scaling Rn to the power minus 1/2, 0.55, which is inconsistent. It was never predicted by any model. The origin of this is still unknown. And the integral scale shows no dependence on Rm as expected, because it's just integral scale of 2 Now, this is the planarity versus filamentarity. As we can see, as Rm increases, this is the path our structures make in the planarity filamentarity plane. First, we see that, say here, planarity is 0.1, filamentarity is 0.2. So they are more like filaments, but not very strongly. For Rm equal to 1500, it's already filamentarity is factor of 2 larger than planarity. And you can show that for these are our fits for planarity and filamentarity. For Rm larger than 200, filamentarity will be much larger than planarity. Then you conclude that what you see are in fact dominated by filaments. No doubt, no arguments. Don't worry. It's a good, reliable result. You know the morphology of what you have in your computing box. Remarkably, the corresponding values for the current isosurfaces look like ribbons. Filamentarity and planarity planarity and filamentarity are very similar. Filamentarity is slightly larger. This is typical of a ribbon. Not surprising, right? If your magnetic field is in the filament, the current will be on a surface surrounding it, right? So the current then, by definition, will be on the surface. This is exactly what you get here. Now, another question. When you want to decide what's the morphology of your structures, at what level should you plot the isosurfaces? Different people do different. How can you decide? It's obvious that if I plot isosurface at a very high level, for example, imagine that I have a box with the average value of whatever else variable equal to 1. And the scatter, the standard deviation, is 1. And I will plot isosurfaces where my variable is equal to 27. If I'm lucky, there will be one single point with this high value of my solution. And of course, this point will be quasi-spherical. So at a very high level, isosurfaces will always be spherical. if I now reduce the level and come to the level near the average, it will look like this flow. It will be, the volume will be filled with surfaces at the lower level close to the average, just because the average value you encounter most often. So it's clear that the morphology will depend on the level at which you consider it, the level of the surface. Clever and experienced people intuitively choose the right range of the levels where they do as a surface. But still, of course it's good to be clever and experienced, but what if you are not? Better to calculate the range of, suppose you have a random quantity, say D, equal to B naught, I mean RMS values, plus sigma D times random quantity. I know B naught and sigma D. At what level, how I choose, I want now to draw this surface S, where D is equal to B naught plus alpha sigma D. So alpha is some number I'm choosing. At what level I draw my other surface. Should I take alpha equal to 1, 5, 27, 3 sigmas, 5 sigmas, half a sigma? What level I should choose? And here, with this approach, you can just answer this question quantitatively. Here we plotted the thickness, width, and length of our structures as a function of this alpha. At small alpha, or for the 1, of course you have complete mass. This is exactly where your box looks roughly like this sponge. At higher values of alpha, everything will become varying very strongly. But there is a range from 5 to 5, from 2 to 5, where the variation of these parameters is negligible. You cannot see anything unpleasant here, but there will be, if you look closer, as Louis Wilkin did, there are unpleasant behaviors here. So this is the working range. If you have a random quantity in your box, and you want to plot its isosurfaces, choose the level equal to the mean value plus 2 or 3 or 4, perhaps 5, values of the standard deviation. Don't take 10, don't take 1.
So asterisks are what?
These are the measurements.
Yeah, asterisks, which correspond.
Well, I don't know, but they are all so close to each other.
Yeah, they're also close to 0.
Is that
Yeah, because its Rm is large, it's linear.
Is that a universal solution, or is that for a particular set of data?
I don't know.
Analyzing set of
This I don't know. This I don't know. We had this experience with this specific data set. But on the other hand, this is exactly what experienced and clever people do, right? But they do it intuitively, but better to check if you plot your isosurfaces. With Minkowski functions, you straightforwardly make this plot to confirm that what you are discussing is meaningful, that you are not somewhere here or somewhere here. It's just a matter of calculating a few integrals, and then you know where you are. You choose then reasonably this level. What an advantage. Instead of looking for a black cat in a dark room, you have everything under control. And I should say that the pencil code, the pencil code already has a module which does calculate Minkowski functionals for a given data field, correct?
It's not checked in.
It is there, yeah.
It was done.
Somebody look at it.
Yes, Tony, me, and then Snowden. And MATLAB now has built-in routines for calculating all these integrals. So with MATLAB, you can also do it just by pressing various buttons without thinking. It will think for you. Or somebody has to. That's it. Thank you. Sorry.
Thank you. Thank you, Anwar, for bringing us to a broad spectrum of different topics within the broad range of galactic physics. Questions, please.
Good. I bored everybody to death.
One sigma thing, although you not look at radius, which is the most important for many observations, because you want to know how volume filling the field is on the average, right? I mean,
Congress, what the question is, will be this level mode independent or even realization independent. Right? If it turned out that it's important for observations but meaningless physically, then you better change observations. It cannot be done quickly, but what?
So what I mean is, if you are taking 3 times or 5 times the RMS, although visually this is what people plot, I'm against this for the following reason, because you just show what is very rare things rather than what is most common.
No, but it's clear why this happens, right? Because 3 sigma means 97.5% for the Gaussian linear variable. This means that if we have a three-dimensional box, then the volume filling factor of the structures for Gaussian distribution will be order of 3%. This means you can see very nicely through the whole box. If you choose the level of 1 sigma, it will be a mess which is difficult to publish because you can see nothing. Because the box will be too full of structures.
But then one has to ask for a given observation. For example, if you take synchrotron emission in this field or rotation measure in this field, what is the thing which is contributing to that observation? And one would like to know, for example, if all the 1 sigma things are reversible, then the rotation measure will cancel or something like that. So you need to think a little bit.
Yeah. But this is in fact exactly why I really, when I read papers where only nice pictures are given, it irritates me enormously. Because these nice pictures most often, not always, represent rare events. Like, well, there it was the isocontours I was showing you look nice only because, as Andrew says, the rare events. That Q, it was the 3 sigma level. So rare occasions. If you plot 1 sigma, it will be totally uninformed as a nice picture. But this exactly the data you should publish as numbers, as one-dimensional graphs, which look boring but contain more information than many colorful pictures. Very often, not always. I'm not making general statements. But it is a problem now, at least to me, in many papers where people publish very skillfully done colorful pictures that don't provide elementary estimates. For example, the random quantity is discussed. What is its mean value? What is the standard deviation? Does it have a Gaussian distribution or not? Almost nobody does it. And then this means that if the data are useless, you cannot use them. Just because only colorful pictures. Very often even without the color bar. Yeah, I agree with you, but such data can be presented in the form of pictures. They can be presented in the form of tables, in the form of simple two-dimensional graphs, black and white.
Just double check that indeed this Minkowski stuff is not in the pencil code. So that is one of the examples, of course, where if a student accomplishes great work and does something, it's good if it has actually a solid and reproducible entry somewhere.
This is true. But Andrew, wasn't it?
It's in the IDL routines.
Oh, it's in the IDL routines, yeah?
But you can translate from that code to C.
Not me.
I was looking.
But I can give you an email or a postdoc in Newcastle. Who is doing it?
MATLAB as a C translator.
Oh, yes.
You take a MATLAB function and you see MATLAB.
I think also Fortran, right? Also understands Fortran.
Wow, there's it Minkowski, yes. You're right, Anwar.
Oh!
So that was quoted by Andrew Bagley. Right? Shape finder. Thanks for alerting me to that. And I think it would be a great thing to do it actually online, because these are just numbers, so you can get it as a function of time from the entire box then.
Mm-hmm.
And it's really not a long routine, you see. And it's all public. Anyway.
But the advantages,
So
I hope I have convinced you.
Thanks to the new
The advantages are enormous.
Yes.
The effort to calculate them is finite. Anyway, I have to do it once to write this piece of code, or just take this one. But the advantages are enormous. Okay, coffee break.
Now we have the coffee break. Let me also remind you of the student presentations that we have now. We have 3 presentations lined up. They will all in this room. If somebody was forgotten, please talk to me. There might be a short possibility for a short slot, but I rather think not. Instead, we will have, starting at around about 6 o'clock, or when we are ready here, we will start with some drinks downstairs in the 3rd floor, and we'll have the conference of full dinner in the auditorium 32. So that's really prepared by the secretaries and by Hans, hopefully in a pleasant way tonight.
32 in this building.
In this building.
Is there a projector in this?
You want to give a...
Just in case.
Yeah, there's a projector, you know. So, good. Then we have...